Hello, everyone. Welcome to the seminar on a particular topic on physics. We are we are joined here by Kazi. Kazi is pursuing MS PhD in IACS Calcutta, and we will be discussing a very interesting topic in modern physics. In fact, we will be discussing a particular experiment, very seminal experiment in the world of physics. So, Kazi, go ahead and why don't you tell us what the experiment is about?
Okay. So, good afternoon, everyone. So, today what we are going to actually discuss is we are going to discuss how this particle nature of light was developed into the wave nature of light. And in this particular transition, the most important experiment was Young's double slit experiment. So maybe you guys have heard about this particular thing, but the thing is that it is not how just one single experiment can do this whole transition. There was a whole story of this particular thing and how this experiment is in its way so much beautiful. So today we are basically focusing on this particular part. So let's start this particular thing. So today our main topic is actually the history of wave nature of light. So we basically know that light is wave. I mean, in nowadays it is, not so much obvious. I mean, normally just you guys can think, okay, so we know that light is actually a wave, but it was not obvious from the very development of this particular idea of light in physics. So the story starts like this, that initially actually light was not actually assumed to be a wave. It was actually assumed to be a stream of particles. And this particular thing was actually described by Sir Isaac Newton in his book. And this particular theory was actually at some point, especially in this 1704, he actually has written his actually supported this particular idea openly. So his idea was very simple, that every source of light actually emits small particles like balls. Okay. And this particular idea was, you basically expect this from Newton, right? Because Newton was a man who basically do this all of his job with point particles, from starting from Newton's first law to his gravitational law. So basically, we expect that Newton will always do something like talk about these tiny particles. Everything he want to explain it in terms of particles. So basically, he does the same thing for the light. So he assumed that light is made out of small balls, a very tiny balls, and it can be thought of like this: that we have basically like this a source here, and from this particular source this particular source uniformly emit small particles, and this was his assumption. The other thing which he assumed is that these particles are perfectly elastic. I hope we guys are familiar with what we mean by elastic. That is, after a collision, whatever velocity it was going, it will return with the same velocity. So elastic means the
So this is like
momentum
a
and the kinetic. Yes,
so this is like a technical definition of elasticity. Perfectly
exactly.
elastic means after collision it comes back with the same velocity without
Yes.
any
So
loss of velocity in some sense. Yeah.
exactly. So actually, this perfect elastic means that after the collision, the total momentum and the total kinetic energy both be conserved. So it is like the ideal case, like ideal
I,
gases, ideal collisions, something like that.
okay.
So they assumed it like he assumed it like this, and he also assumed that they will be rigid and weightless. Fine. And using this particular assumption, he actually can basically explain why this particular law of reflection happens. Like we know the law of reflection, right? That if there is some sort of plane and this is the perpendicular, light ray can come like this, and uh, it can actually reflect, and the angle between those two things will be exactly the same, like here. These
Right.
two angles will be exactly equal. So that is what do we mean by the laws of reflection. So basically Newton's law this particular thing actually helped in proving this particular things. If we try to do this particular thing a little bit in much more detail, then the thing is that he can also explain this refraction. What do we mean by refraction? That is basically same like reflection, but the core difference was that these two mediums will be different. So this is one medium and this is another medium, and let's say this is the perpendicular. So light can come and it can actually go into the medium. And what will be the relation between these angles? This angle and this angle. We know the Snell's law. It describes this particular thing. But see, when Newton tried to describe this particular thing, there was actually the fault. Some particular faults were coming. To actually prove this refraction, Newton has to assume some sort of extra force, which is in between these two mediums, which can automatically accelerate the particles. So what Newton assumed is that the velocity of light in air is actually less than the velocity of light in water. But nowadays we know it is not the case. Actually, in water, the velocity decreases. So it was one of this particular point which Newton has to assume to prove this particular thing, that the light has to bend towards the perpendicular. Okay, but it is not the all. It is not all about this particular formula. It is not all about this particular theorem. The theory actually tells you something more. It tells you that, suppose like in this particular diagram, we can clearly see this is a source. Now, if by any source it actually emits like point particles, what will happen in this particular cases? If I have a particular object which is like beside which this particular source is, those particular particles cannot actually go in this region, right?
Right.
The object will completely block the
So
particle.
maybe
It's like suppose you have some,
if there is a sheet of glass, maybe then the
yes,
particles cannot really penetrate the glass, right? I mean, they have to sort of bounce back.
exactly. But see, when there is like a transparent object, Newton assumed that for transparent object, they can actually go through. It is like when you take some opaque, that is objects which completely block the light. For those particular cases, what will
Okay.
happen? They will come and just bounce back. That is the whole idea, because they are balls. It's like you take some balls and you throw it to the wall, they will completely bounce back, right? If I have a particular line, let's say, and I throw like hundreds of balls, what will happen? This particular part, at this particular region, there will be no balls. Every ball will hit the other particular regions, right?
Right,
So this
right.
is basically what our common sense tells us. But
Uh-huh.
there is a little bit of problem with this particular thing, and the people of that particular era actually point out this particular problems, but it was like Newton was saying something, so how can it be wrong? So there was
Right.
like this particular type of thinking, and in the world of science this should not be the case. Always think rationally, everything. If something is wrong, tell it is wrong. That's how we learn maths and physics, maybe any stream, chemistry, biology. So at that time people were not that brave. But there is another particular problem which I want to point out. See, suppose you guys can see in my video, the light is here in this particular site. So this particular part is visible, but it's not like this particular part is not visible. It is also a little bit visible, right? It's like
Right.
a source is here, like in this particular picture, the light is in this particular region. But this particular kid can actually read out its book. But from this
Right.
particular theory of light, which Newton actually proposed, light should not go in that particular region, right, where the book is, the part which he is reading. It should not be the case. So how can we actually read this particular thing? So actually, Newton's theorem tells us, or Newton's theory tells us, that the shadow should be completely pitch dark.
I
It
see. I
should
see.
not be like gray or maybe a little bit of color, right? Because if we have particle, it can either go or it can completely be blocked. There is no in between thing.
Right.
So we can actually try to understand this particular thing in much more detail. So like in this particular next slide, we can clearly see this particular thing. So normally what we see that shadows are not completely dark. You can actually see things in the shadows. You can see few details in the shadows. So this is not something which Newton's theory actually suggests. And what is the reason of this? The reason is actually something which comes much times later in, if you see it historically. The reason is two particular terms. One is scattering and the other one is diffraction. So if I want to tell about it a little bit, so you can actually understand it like this, that suppose I have some object like some book, light is coming. See, in this particular part, what will happen? The light is basically coming in this particular region, right? So the phenomena where along the sharp turning points, light can bend. This particular phenomena in simple terms is called diffraction. Okay.
Okay.
So basically, it should be pretty much obvious that normally when we read things, and most of the times in our life, diffraction actually is much more important, right? For seeing different type of things.
Right.
And this is actually a fact. This particular image is taken from in moon. So here you can see actually that the shadows are much more dark. So why this happens? This happens due to a phenomena called scattering. What is scattering? So in simple terms, again, scattering is something like, suppose there are few dust particles in here. So when light comes, these particular particles can absorb the light and can again emit the light.
Okay.
So absorb and again emit. Suppose I give you some candies, you take it and you distribute these particular things, something like that. So in moon, there is no atmosphere, no air. That's why this scattering phenomenon is that much, it's not present there. And only diffraction is there. So the shadows are much more dark in that particular sense.
So we could have sort of titled this particular video, part of the video, as "Why Shadows in the Moon Are Darker." That's kind
Yes,
of nice.
absolutely. Yes. Because you see, physics is hidden everywhere, from
Right.
everywhere. So we just have to think these particular things. Like
Okay.
just
Yeah.
basically by just understanding this particular thing, just by pointing out what Newton's theory cannot explain, we are basically understanding why shadows are pitch dark in moon, something like that.
It's very nice. Yeah. Then.
So like I said that in moons, the shadows are almost like pitch dark because there is only diffraction, not the scattering. So
Okay.
in the next slide, there is actually a little bit of picture of scattering. What happens? That is when sun's light comes in, our atmosphere, there are many type of gases, many type of dust particles, carbons. So they actually absorb this particular light and then can re-emit. So that is basically what do we mean by scattering. And basically scattering is our favorite because in my institute, Sir C.V. Raman actually experimentally shown Raman effect, which is related to scattering. And that was the first Nobel Prize in India in physics. So basically scattering, we love scattering. Okay. So this is something like scattering, which I told. And this is one of this particular point, which actually tells that, okay, so Newton's law may not be correct. So maybe there is something where Newton is also wrong. So to explain this particular phenomena, which I said, we actually need waves. Okay. And here comes this gentleman, and he in 1960 published the wave theory of light. And I am sure most of the students who are reading this wave nature may have actually read his laws.
Okay.
So what does,
1690. You mean 1690?
yes, 1690, sorry, yes.
Right.
So what does his law tell? So his law basically tells that light is actually a wave, and what happens is that depending upon the shape of the source, it emits different type of waves. like if I have a point particle, what will happen? It will uniformly emit spherical waves. That is, surfaces of sphere are going out of that particular point.
Okay.
And each point of this particular waves can actually act like secondary waves. And if I draw the envelope, that is the path along each of these particular emitted secondary waves, they will form again a sphere. We can prove basically that particular thing. And this particular image actually shows something like that. But see, there is a little bit difference in physics. In maths, what happens? You can do abstract things. But in physics, it is not so. The foundation of physics is always try to do experiment. No matter how great or how beautiful, how elegant your theory is, if it does not, no experimental evidence are there, it has to be wrong. We cannot accept that particular thing. Like maybe if some particular interested students are there, maybe they have heard about string theory. Okay, so string theory, very nice, interesting, but it is not experimentally verified. So people does not actually take into account that as a particular theory yet. Maybe in future we can have some proofs, but not yet. So exactly that happens in this era too. When he proposed this wave theory of light, there was no experimental evidence. He give that particular theory. That particular theory can very nicely explain reflection, refraction without assuming anything. And also the assume whatever the results were, like the water's velocity in denser medium have to be lower. His actually theory suggested those particular things. So all of this is fine. But again, no experimental evidence. This means no taking this particular theory seriously. And also there is Newton, whom he is opposing. Huygens, I mean, he is just a new guy who is doing a little bit of physics, and there is Newton, who discovered calculus, gravitational law. So how can he stand before him? So
Right.
something like that. So in that time, many people opposes him and his theory. But again, if something is true, in some time there will be evidences. And this particular point I want to tell. See, most of the people thinks, and our today's goal is also this double slit experiment, but it was not actually the double slit experiment which actually suggested initially that light is a wave. It was actually some related to diffraction, and actually it was performed by this particular guy.
Grimaldi.
So
Okay.
yes, so when this guy actually performed his experiment, and this whole scientific community was talking about that, and his experiment was something like this. So he made a small hole, small aperture, and he let light go through that aperture in a dark room. Okay, and then there was a second aperture, a second hole, and then by going through the first aperture, then the second aperture, the light falls on the screen. That was basically his experiment. Okay, so maybe if I try to draw it here, so light is coming, there was one hole and there is another hole. So light comes and then it falls on the screen. So something like that. Okay, now he noticed that the center of light was actually bigger than the size of the aperture. That means light is actually diffusing. Okay, so what do we mean is that something like that. So maybe the second aperture size was 1 centimeter. So when the light was falling on the screen, the size of the bright spot was actually greater than this width. But it should not be the
Okay.
case, right? If lights are particles,
Right.
it should be exactly of the same shape.
Right. Right.
Okay.
Right.
And also there were different color fringes, that is a different type of shapes of different color. So actually the result was something like this. Very beautiful. Okay. So
Yeah.
this was like his result, and it actually intrigued Newton so much that actually Newton performed the same experiment. And he was, I mean, saying like, thinking like maybe that, okay, so I am getting like this. Can I explain it using my theory? I mean, we know Newton was very humble guy, but it was genuinely not true. He was
Yeah.
very arrogant, and maybe people have read the stories about this particular thing. The famous story where actually Bernoulli challenged Newton to actually solve a differential equation. So things like that. So he is too much arrogant, but yes, still, when you are that much genius, it is accepted that you will have some arrogance. So he was still not convinced. He was saying, no, no, no. Maybe I can explain these things using my theory. Don't have to go about this wave theory. But later then comes this guy Young, a young genius, Young, Thomas Young, and basically he was said to be the last man who knows everything. So when in his era, the science has not developed that much. There was normally going on with classical mechanics. In maths too, there was a little bit of complex analysis and things were going on. Okay, maybe there was a little bit of different particular things in physics, chemistry, biology, whatever. But see, each field has not developed that much. So from his point of view, whatever exists in his era, he almost know everything. So this title was given to him because of this particular reason, that the last man who knows everything. And he was basically a genius. So see, what Young done has actually a huge physical significance. Why? Because you see, his experiment was like this, which he performed in 1801. So in his original experiment, again, a little bit of misconception, which most of the guys have. Young's original experiment never contains two slits. It was actually two holes. That's why I have written Young's double hole experiment.
Okay, okay.
So there were basically two holes, and he was throwing light through that particular hole. And there was a screen on which the light falls. Okay. Now, what does the particle nature tells us? The particle nature, if I try to show you guys a little bit of it theory, see, if I throw small bullets, what will happen? The bullets will go. So the bullets will go through this particular hole, and maybe they will fall at this particular region, right? And the bullets which go through this hole, they will only fall on this particular region, right? So
Right,
the part where light falls should be two regions only. This region and this region, nothing more.
right, right.
That should be basically the case. I mean, at least my common sense tells me this, right? Tells me this. And if someone is interested, they can actually read the book of Feynman's lecture, volume 1. There, a very nice illustration is given about this particular experiment. So see, what actually happened is pretty much interesting. Why? Because the thing which was actually seen, the distribution of this light was actually like this. So light was not only in two places, but rather it was distributed. Some places brighter, some places darker. Again, some places brighter, some places darker, like
Right.
shown here. But how this can happen? Where can I see this type of phenomena? See, like here it is shown. This type of phenomena can be only noticed if light is a wave. You can basically perform this experiment with a bucket of water. Let's take a bucket of water. You take a paper, you cut paper in the paper two holes and just dip it such that there were two openings. And then you just in two places forward that particular slit, you just disturb that particular water. You will see basically this type of patterns in water.
Right,
See,
right. Yeah,
in these particular places, there was maximum, right? The waves are combining.
yeah,
Superposition is happening. And in
yeah.
some places, the waves are actually destructive, doing some destructive interference. That means if one wave is like this, the other wave is like this. So they cancel each other.
Uh,
So that is actually the reason why this Young's experiment is so much powerful. We have to understand this Young experiment, whatever is this particular phenomena, this whole phenomena is actually only possible if upon whatever thing you are doing this particular experiment, with which you are doing this Young's experiment. Maybe it is water, maybe it is oil, maybe it is light, or maybe a little bit of spoiler, maybe electrons, which we will talk about maybe in the next session. So
Yeah.
this particular experiment, whenever we perform this experiment and we see this type of pattern, it suggests, and I repeat, it must suggest that that particular object is a wave, because only waves can bend in the. So see, like I said, diffractions is something like where they can bend towards the shape, right? So it is becoming obvious, right, that okay, so light shows diffraction and interference, so there must be a wave. And I have a particular video which I was not able to add in this particular thing, but maybe I can show you guys. So this is actually an experiment performed in water. So you can see what was I saying. So I have this source going on, and there are two slits, two holes in the water. And when this water is going through, some places it is combining, some places it is destroying each other. And we are basically seeing this exact pattern which we normally see in Young's double slit experiment. See this particular pattern.
Right.
This is, like you can clearly see, is a property which is only shown by liquids, or not liquids, waves, sorry. So sound wave can also show this type of property, and basically we can show that too. We can do experiments, and I will encourage you guys to actually do this particular experiment. Okay, so this was this particular case, and in your home you can actually perform this particular experiment. You can take a piece of paper and you can paint some particular part black. Why black? Because you see black color actually absorb extra amount of light. So you take two slits and the other part is colored black, so it will absorb remaining part of light. So this is like this, and you can basically see a pattern like this. Okay, so this pattern is a little bit different, but similar to that. So you guys can actually perform this particular experiment. But see, this particular thing is not all. The thing is that at that, so there is a very nice quote by Carl Sagan, one of my favorite scientists, astronomer. So what he says, extraordinary claims require extraordinary evidences. So such a beautiful quote. I mean, see, at that period of time, Newton was the extraordinary guy. He have discovered so many things. And later I will show you a few names who were supporting this Newton. And I mean, basically, the physics giants were supporting Newton. So how can he be wrong? So to prove Newton wrong, you have to submit some extraordinary evidence. So, and this particular time in 1880, so this year, French Academy of Science actually held a competition to explain few properties of light. And this guy, an engineer, we don't like engineers, especially from the point of view of physics. They approximate pi as 3, but no, it is not possible. I mean, sir also agrees, right?
I don't know. It's a very controversial question, I guess. Yeah.
So
Yeah.
this guy was an engineer, Fresnel.
Mhm.
He is a phenomenal genius. Why? Because you see, he also said, okay, so maybe I am an engineer. So, but let's apply in this particular competition. Maybe I can win. So he actually submitted his theory on wave nature of light. Nice. But see, this giant came, Poisson, starting from complex analysis to electrodynamics, electrostat electrodynamics, every era, fluid mechanics, in every part, this guy actually, I mean, completely rocks. I mean, basically, people who read maths and physics, I am pretty sure they are familiar with this guy.
Yeah, Poisson, of
This
course.
guy supported particle nature of light, and he was one of the judges of this particular competition.
Okay.
Now the problem arises. He said that, okay, so he is saying wave. So, okay, so let's just completely just destroy him. He says, okay, so if your words are right and light is a wave, then what should happen? If I have a circular object and light is coming from here, and suppose there is a region where shadow is being casted,
Uh-huh.
the shadow is here. In between this particular region, like here, there should be the bright spot.
Right.
With
Because
this,
of
so
different
he
days.
suggested, he showed that if light is a wave, this should be the case.
Right.
It was the complete, I mean, complete breakdown of Fresnel. I mean, we does not see like that type of bright spot. So how can this happen? And if someone is curious why it should be the case, let me again show another simulation. I mean, I love simulations and programmings. So you have to bear that with me. So let me actually, okay, so this is thing. So I have a particular part, a sphere, light is coming, waves are coming, waves. So they will act like you just see water waves. They will bend in this particular region. And you see, due to this bending, this particular region seems like it will get brighter, right? And it is
Right.
strange. It should not be the case. But if light is a wave, this should be the case.
Right.
I mean, it is pretty much counterintuitive. I mean, if you ask me, pretty much counterintuitive.
Yeah.
But like this is the complete breakdown of Fresnel. I mean, how can he oppose? He have never seen things like that. And it was pure victory of Poisson. He is like, okay, so I win. There was no bright
Yeah.
spot in the between region. So I completely just destroyed this wave theory people. Okay. But see, this was an extraordinary claim, like I said. Wave nature of light, extraordinary claim. We need extraordinary evidence, and the thing was completely just beautifully just I mean arranged by Poisson. What happened is that in that particular competition there was this particular guy which is Argo. So Argo was actually committee head, and while going through these particular things and discussing, he was actually pretty much curious with this Fresnel's idea and Poisson's, I mean, counterintuitive thing. And he said, okay, so let's just do an experiment. In physics, just do experiment. If I don't get that, then it is wrong. Then particle nature is the winner. But what he saw was actually pretty interesting. He saw that indeed we can actually get a bright spot in between the shadow.
Right.
And let me tell you that the interesting thing was that, okay, so in the previous slide, let me come to the previous slide. So this particular spot was sometimes called Argo Spot because he was done the things. But if you read some standard textbooks like Ajoy Ghotok's optics book, or maybe in Google or everything, you will see that this spot is actually called Poisson spot. Why? Because he was the one who actually coined this particular thought experiment. And let me show you actual experiment which was actually performed in the laboratory. So we can very easily do this, and in some places it was actually performed. So see, these are two lenses which will just magnify this whole thing. So I have a penny here, and I will take that penny and keep it in that particular region. So light is coming from this side. In this side, there will be a shadow casted, and that particular screen is shown here. Okay.
Uh,
So now when I put this particular ring, can you see a bright spot in the middle?
Yeah, yeah, I do see it.
So,
That's
I mean,
fantastic.
how beautiful this particular thing is. There was an extraordinary claim. They tried to, I mean, totally cut down this particular claim, and they talk something pretty much, I mean, at that particular time, it was pretty much rubbish. And that particular rubbish thing becomes the extraordinary evidence, which showed
Right.
that what they actually said is indeed true. It has to be true.
This is fantastic. Yeah. I
Yes,
think
I mean, this, yes,
yeah, I think this is one of those extraordinary proofs that you mentioned, right? Like
yes, exactly.
yeah.
So, see, I mean, this was not actually always performed, but the double slit experiment is actually the most nicest one. Why? Because this double slit experiment is one of the most easiest thing which we can actually do. But
I
it
see.
is not all. The here is there is more. In physics, there is also always the more things. So now I want the watchers or viewers, whatever there are these peoples, I want for you guys that let's perform this particular experiment. Try to perform this particular experiment. And sorry, there will be one laser. So what? And also doing this particular experiment, when I will describe it, always wear protective glasses because I don't want our viewers to be blind. Okay.
Right.
So the first thing is that you take two blades and you
Okay.
make these particular blades very close to one another. There is very narrow slit there. And you take your laser and point it in this particular region. What you will see? If you do this, you will see this type of pattern. This particular pattern again can be only be explained using waves, and this is called diffraction
Right.
pattern, and it is a single slit. Okay. Now this is not all. See, this is actually much more funny thing, and I want you guys to actually also perform this one. Maybe you guys can actually do these experiments and maybe write some blogs and maybe share with us. So what this
Uh-huh.
particular experiment is, this experiment is that using this diffraction, you can actually measure the thickness of hair. Something not related to this, we have established that light is a wave by interference, double slit experiment, double slit interference, and Poisson spot. But still, we can actually do few funny things, interesting things, because physics is not just always about doing calculations and just doing experiments, rigorous experiments. No, sometimes do it for fun. So what
Yeah.
you can do is you can actually measure the thickness of your hair using diffraction. The idea
Okay.
was very simple. So let me describe the particular experiment. The experiment is that, so you like take a cardboard like shown here, and there is this hair attached there. Nice. What you do? You take a laser and you focus it on the hair, not side, on the hair. What you will see that there is a pattern created like this. So this particular experiment was done by two different lasers, and this is the diffraction pattern. What you can do is you can measure this length, so the distance between maybe this and this, two diffraction, two minimas, two first minimas. Okay, so what I'm saying is that in the screen the pattern is like this. So you measure this length, and by measuring this length we can basically just measure the thickness or diameter of our hair, and these are few results which I have just shown here. Okay,
Okay.
so and how we basically do it, so maybe I can actually explain it a little bit. So this is my laser. Here is my here maybe is my hair, and here the diffraction pattern has been created. So this is the center, the highest bright spot. This angle, let's call it theta. This distance between the wall and your hair, wherever your hair was present, let's call it d. Okay, and this angle is theta. Then the formula is actually thickness of the hair will be simply lambda into sine theta. Oh, sorry, lambda into sine theta. So by just measuring this particular distance, that is this half distance, and you already have the knowledge of this d, you can measure, you can take the value of this theta, right? You can find out the tan theta. Once you have the tan theta, you can find out the sine theta. Have
Right.
the sine theta, put it in the equation, you will get the measurement of the thickness of your hair. How
Right.
beautiful this thing is. So, and hence we actually by this particular discussion proved that okay, so light is actually a wave. But again, see, I have not written here that light is actually a wave. I have written here light is something which behaves like waves. Why?
Right.
Because maybe later we will see that light is
Yes.
also a particle. In quantum mechanics, we have seen this using the photoelectric effect. So what is it? So people say that okay, so sometimes light behaves, sometimes light is wave, sometimes light is particles. It is completely wrong. See, it's like I remember one particular story which my grandfather told me. So he was also a teacher of physics, and I love to listen his stories. So he was like, so when he was actually talking about this particular phenomena in my childhood, so he said that, so okay, so let's see. So there was a story where there were three blind peoples, and they live in a village. And on that particular village, one day elephant came. A guy with an elephant came, and they want to see how this elephant look like. So these three people go, and one people was actually standing in the face of this particular elephant. The other guy was close to its ear, and the other guy was close to his legs. So they touched it. When they touched it, the first guy hold his trunk. So he says, okay, so elephant is something maybe like snake. The other guy, when he hold his elephant's ear, he say, okay, so maybe elephant is like very thin animal. And the other guy is whatever what you are guys are saying. Elephant is very, I mean, very fat. So much I was not able to hold the whole elephant with my hands. See, all of these guys are not wrong. They were never wrong. They all describe elephant correctly, but from different places, from different point of views. So
Right.
still physics is not, in physics it is not clear that what light is. It is not
Right.
clear what light is. It is up to this particular point we only know that light is something like the elephant, and we are like these blind peoples. We sometimes see that maybe okay, so maybe in some cases light behaves like waves, and in some cases light behaves like particles. But maybe it is something where you can think it like that. Maybe we are just looking into its face, and maybe we are some places sometimes when we are standing behind the elephant, and we are just
Right.
basically seeing this thing. So light is something which behaves like waves and particles. Neither Newton was completely wrong, but okay, his theory was wrong. But okay, it is, he is a little bit I mean right, that light was a particle. So
Yeah.
it is basically, the story goes on like this, and
Thank you, Kazi. I
we
mean,
basically think like, yes,
yeah, yeah.
I
This
hope
is really
people enjoy
wonderful.
this.
Yeah, we learned a lot. Thank you to the viewers as well for joining in. I hope to learn more from Kazi about the wonderful world of physics, and he's also a faculty at the physics department at Chinta, so he's doing wonderful work there. I hope to see you guys next time with another seminar on physics, and we will learn something more exciting. Thank you, Kazi,
Yes,
and thank you,
that
everyone.
will be exciting. Yes.
Yeah,
Okay.
bye.